please, Mr. Ćerić, start with your presentation.
Okay, thank you very much, Mr. Chair. It's past noon, so it's safe to say good afternoon to everyone attending this session. Today, I will present in the next 10 or 15 minutes an approximate technique for the delineation of wellhead protection zones in sand and gravel aquifers. So basically the question is why water source protection zones and why simplified techniques? As you all know probably, groundwater is widely used for the water supply, and due to increasing water demand over time and also due to increasing pollution of water resources, many countries nowadays enforce water source protection zones around the wells. And this enforcement typically is applied by establishing one or more protection zones around the wells, and also applying different land use regimes and protective measures within those zones. Clearly, when we are talking about groundwater, due to the complexity of hydrogeological settings, establishing or defining these water source protection zones can be a very complex task. In the recent years, due to rapid development of computer hardware and user-friendly software, it's becoming easier and easier to apply different mathematical models to delineate water source protection zones. But still, simple methods are for many reasons useful. One of the reasons may be to, for example, use stepwise approach in the delineation of wellhead protection zones. Another one is to build modelers' intuitive and better understanding of the results that will eventually come from these sophisticated models. As you all know, sophisticated models are quite complex because we need a lot of data, we need computer tools, we need also trained personnel and modelers, and also we need financial resources. And it's not feasible and practical to apply these sophisticated models every time and in every hydrogeological setting. That's why sometimes applying simple models can be a good starting point for the development of water source protection zones. So having this in mind, today I will present this simplified technique that has been developed for a simplified or simple conceptual model that is presented on the screen behind me. So this is sand and gravel aquifer, homogeneous, isotropic, of an infinite areal extent with a constant thickness, constant coefficient of filtration, in which there is a constant ambient groundwater flow. And in such aquifer we apply a well, perfect well, that is discharged at a constant rate Q, as you see on the screen. Based on this simple conceptual model, I propose a simple technique that is based on exact analytical solutions that have been developed years and decades ago. And this simplified technique will be presented in the following slides. So starting point is analytical solution for time of travel water source protection zones, which are defined by this equation initial equation presented on top of the screen here. This equation is quite old and very well known, and it actually defines, it is a dimensionless equation which defines time of travel, wellhead protection zone, water source protection zone, which means that it defines boundary or isochrone of a zone for which of a zone that has defined that is defined for a certain residence time, and for which all water will eventually or within this resident time will reach the well. So this is time of travel protection zone, which is dimensionless. As you can see, these x and y tilde parameters are coordinates of the protection zone in a dimensionless form. This parameter ls, which is used for normalization of this equation, is actually distance from the well to the stagnation point of the well. I will show it shortly on the next slide. What is this distance? And also T tilde is actually dimensionless residence time, which is defined also using the following equation on the screen. As you can see, this residence time is defined with only a small number of aquifer parameters, and it is actually very easy to calculate for this hydrogeological setting. This initial equation on the top of the screen for an infinitely long residence time simplifies to the bottom equation, which actually defines the boundary of the catchment zone. And this is the line inside which all water will eventually reach the well. So this is actually a graphical presentation of the initial equation on the last screen, which presents a number of water source protection zones for different values of this dimensionless residence time, T tilde. Just looking visually at this this graph, one can see that the shape and size of the water source protection zones change as this dimensionless residence time change, in the manner that for very small residence times, on the order of magnitude less than 0.1, these water source protection zones appear circular and centric to the well. As the residence time increases, again, in the range from 0.1 to 1, these water source protection zones still resemble circles, but now they appear eccentric to the well. And the center of this circle is, or near circle, is moved in the upstream direction, actually into direction of from where the groundwater, ambient groundwater flows. And for residence times larger than 1, these water source protection zones do not appear circle anymore and cannot be reasonably approximated by circles. So based on this, assessment, a simplified technique was proposed for the delineation of the water source protection zones, actually establishing 3 typical shapes of water source protection zones. The first one would be circular and centric water source protection zone. Second one would be circular but eccentric water source protection zone. And the third one as I call it, boat-shaped water source protection zones for residence times larger than 1, with considering this dimensionless parameter t tilde. So going back step by step and considering these 3 typical shapes, here you can see that based on the so-called volumetric method, radius of this shape can be estimated using this equation, the first equation up there, which is not in the dimensionless form. Then the equation is normalized, dividing it by this distance from the well to the stagnation point of the well. But looking at the cursor, this distance Ls is the distance from the well to the stagnation point of the well, which is in dimensionless form always 1. So dividing this radius by this parameter Ls, we get radius in the dimensionless form, again as a function of residence time only. But in this case, this equation is not conservative, the second one, because we ignore, using volumetric method, we ignore ambient groundwater flow. So in order to have a conservative solution, there has to be a correction factor, which is this numerical value 1.15 something, which actually gives fully protective water source protection zone for any T tilde dimensionless residence time, which is smaller than 0.1, which is actually the range that we consider for establishing, in order to establish circular centric water source protection zone. So the graph here presents actually with thick lines. You can see these approximate zones, which are centric with respect to the well, and the thin lines, the corresponding thin lines are exact water source protection zones, actually calculated using equation, initial starting equation from the previous screens. One point that I forgot to mention on the previous screen is that this initial equation is inconvenient because it's in an implicit form, so it requires computational effort to calculate a sufficient number of points to actually establish wellhead protection zone, whereas in this case, this approximate solution is very easy to calculate. It is explicit, and it depends only on one parameter, which is dimensionless residence time. Similarly, when we look at the next case, which is eccentric circular water source protection zone for any residence time between 0.1 and 1, we can establish or we can define a circle around this well, and also define eccentricity of the water source protection zone by evaluating upstream and downstream lengths of the exact water source protection zones, which can be easily derived from the initial equation that was presented on previous slides. But as you can see here, again, these upstream and downstream distances from the well are again in an implicit form, inconvenient to use, and that's why this radius of the water source protection zone and shift from the water source protection zone are then simplified with empirical equation, which is again implicit in terms of the residence time t, dimensionless residence time t. Again, when you look at the graph, you can see that for any case of residence time between 0.1 and 1, these empirical or approximate water source protection zones are protective and conservative. And the third case, or the third typical shape of the water source protection zone would be for any residence time T tilde larger than 1. In that case, we could have seen on previous slides that water source protection zones are elongated and cannot be reasonably approximated by circles, for which reason it is proposed that a so-called boat-shaped water source protection zone is introduced for any such case. In this case, actually, the water source protection zone is defined as the catchment zone, using the equation again for the catchment of the well, and this water source protection zone is cut off at a distance LU or upstream distance from the well, which is again calculated from the initial equation. Again, in this case, this distance, upstream distance of the water source protection zone is in an implicit form, for which reason it is approximated by the second equation, which is now explicit in terms of the residence time T. And you can see with these two examples here that the water source protection zones defined by this solution are protective for any T which is smaller than 2.85, and for any T larger than this value, they are not fully conservative, but they are a fairly good approximation. In conclusion, I would like to emphasize once again that regardless of many sophisticated models that exist nowadays, simple solutions are useful because they give good insight to the modelers of the outcomes of the model that they can expect, and also they can serve as a starting point of the development of more sophisticated models using computer tools. You have seen that this simplified technique is based on three typical shapes of water source protection zones that are actually estimated using explicit, very easy to calculate formulas that are actually estimated based on one single parameter, which is dimensionless residence time T. Of course, one should be careful when using these tools, because they are, although they are simple, they can be misleading in more complex groundwater settings, in which case more sophisticated computer tools should definitely be used. Thank you for your attention.